you have a great coffee break. Okay, now we will continue our session with Dr. Eva. Let me introduce a little bit about Prof. Dr. Eva. Prof. Dr. Eva is a mathematical statistician at the Department of Mathematics of the University of Genoa, Italy since 2007, from where she received her degree in mathematics, and now her PhD degree is in statistics from the University of Warwick in 1997. Her thesis is the first one in algebraic statistics. Her research interests include design and analysis of experiments, mathematical statistics, symbolic method in stochastics. So now I'm welcome Prof. Dr. Eva to give his talk. To give her talk.
Thank you everybody for being here. Can you hear me or did I just listen? Fine. Okay. So my objective with these 3 hours we are together is to give an introduction to the field of algebraic statistics, not only my own research, but give you some hints on what's going on around. Now, the field of algebraic statistics is rather young, as you can see. What's the rationale behind it? What's the driver? Why something is what could be called part of algebraic statistics? Basically, what happened is that many of the objects which are important in probability, in statistics, are actually polynomials. Why? Well, if you know about linear models, you know that these are usually polynomials, or quite often polynomials in the features. Should I use this? Okay. Okay. Good. So, what's the let me start then this reasoning. What's the rationale behind algebraic statistics? Is the fact that many objects, many important things in statistics and probability, under a suitable parameterization, they are actually polynomials or ratios of polynomials. The field that studies polynomials is algebraic geometry. And that's what's the link between these statistics and algebraic geometry, computational algebraic geometry. Now what happened is that there were 2 original papers that started all this business. The first paper is dated, well, it's been published in 1998 in the Annals of Statistics, but actually it was going around in preprint form since 1993. It's it's authored by Percy Diaconis, who is, I don't know if you've heard of him, but he's a very good statistician from Stanford University, and by Bernd Surfels, who is an algebraic geometer. Now, we'll see a little bit about this, where Markov bases were introduced, correct, Nadia? We'll see a little bit about this in the very last lecture. Where instead I come into the area, this area I'm talking to you about, is with the second paper. Okay, let me do like this. If I have to stay near the phone, I do like this. This second paper, authored by Henry Wynne from Warwick University, who was my supervisor in my PhD thesis, and Giovanni Pistone, who was actually my supervisor during my undergraduate, my master thesis. Okay. They seen a link using the same or very similar algebraic tools to those presented here for expressing, for working with the design of experiments. The title is very funny, generalized confounding with probability basis, but that's what happened, that we statisticians were very confused about all this business for quite some time. So, let me start with some very basic. Because I'm told that you're coming from a very different background. So when I'm thinking about an experimental design or just observational, doesn't matter. What I'm thinking of is an n by k array a big matrix, and the rows. In the rows, I put the individuals, the items, and in the columns, the features, the variables. That is, what I have here, for example, is what have I observed for my first individual. Here we'll have observed height, number of times it's gonna grow, color of cars, things like that. Okay? And I repeatedly do this for all my individuals in my data set. At times, n, the number of rows, is much larger than, or larger just than the number of columns. So we'll have a long matrix, and that's what's standard, let's say, in statistics. But there are some new interesting data sets where our array is actually horizontal stripe. And the techniques are changing. What the statistician can do with that is changing quite a lot. Now consider that in this array there could be empty cells, missing values. They might be missing at random. They might be missing because we cannot observe that. Or we cannot miss it just because we didn't have time to observe that. Or there were some other reasons why we couldn't. There is an interesting adaptation of algebraic statistics to this case. Just for simplicity, we will not consider it here. But if you're interested, I can address you to the research papers that deal with that. Okay. Given that this set of, at the end of the day, will be numbers, organized in this way, what the statistical paradigm is to assume that this array is an instantiation, or each row of this array is an instantiation of a random vector. We call it x. Are we okay with this expression? Fantastic. Then, what's a statistical model? Well, a statistical model for essentially my data, or more precisely for my random vector x, is a set of densities law, density probabilities, for x. Sometimes I can index this set, capital F, via a parameter set, which is a subset of a vector space. Okay? And that, in this case, we'll talk about parametric statistical models. And this is the area where we'll move in. Now, after this preamble, let's say, let's talk about the design of experiment and algebraic statistics. The key point is thus to represent such an array as a set of polynomials. After we've done that, we can use all the theory that Professor Riccomagno explained us this morning and yesterday. We'll do this link with the connection from observed points to polynomials in at least two ways. One, we call it ideal of points, and the other one, indicator functions. And via examples, I will show how to do these links, and I will give some examples of how or where it has been used, what for. Okay, let's start with then the ideal of point item. Just for simplicity, and so that you can see some computations going on, let's assume to have only 4 points in 2 dimensions. A very trivial example. But everything that works here can be carried on n k, n data points in k dimension, no problem. And it can be do that in linear time. That's important. Okay, we have these 4 points, our very simple design, and we say, we look at this design as the zero set of this system of polynomials. You can see that the G1 and G2 polynomials are just telling me, G1 is telling me, look, in your design, the x variable has 4 levels, 0, 2, 4, and 3. The y variable has 3 levels, I beg your pardon, 0, 2, 4. And then what are these? Well, either your points are lying here, on this line, and once they are lying on this line, you can either cut them here, okay, or here. Are these 4 polynomials that we have described this by hand be found automatically for any set of points? Yes. There are functions like this one, ideal of points, in this special software called the Cocoa, but there are similar functions of ideal points that allow us to move from this set to this, which is good enough, and I'll tell you in a minute why it's good enough. So in Maple, for example, I know in Mathematica now they are building one such a function. Okay, so once we have this, we can consider this set as a generator set of the ideal associated with the point. So we moved from these 4 points, say it capital D, to the set of polynomials, ideal of D, whose zeros are all and only these design points. Okay? From an algebraic variety, from an affine algebraic set, to a polynomial ideal. Once we have this, we can say, okay, if I am a statistician and all the information available are here, what can I do? Well, I can consider the set of functions defined over my points. And that's the maximum thing I can say. So this function is called, has been named, called 1 hour ago, the coordinate ring of the variety. The variety, the algebraic variety, the affine algebraic set is very simple now. It's a final set of distinct points, but not necessarily distinct. This is again a slight modification of the theory when we have replicating points that we will not consider here. So the set of functions then defined over my points, here for simplicity I take over the real values, is isomorphic as a vector space over the real, which I consider to be my coefficient ring. It's isomorphic then to the quotient space of all the polynomials in my k variables, quotiented by the ideal of D. This is actually the entry point into this field, this equivalence relation. Now, the important thing is that we can operate by looking, we can operate in this ring and then move back into this, which is where we want to stay as a statistician. We can operate by tools from computational algebraic geometry called Grobner bases. Grobner bases are very special generators of the ideal of D, very special generators of a polynomial ideal. Do you know about them? Okay, so I'll go on the board for 1 minute. First I write something and then we'll comment it together. I give you the definition slightly generally. I don't care if I have an ideal of points or any polynomial ideal. Okay. Let's consider a polynomial ideal that we call ideal, and then let's consider its subset, G. Take it finite. We say that G is a Grobner basis if, okay, take tau, it's a Grobner basis with respect to tau, so I need to define tau. Tau is a monomial ordering. What's a monomial ordering? No? Okay. A monomial ordering is a way to organize our monomials. It's an order on the set of monomials. It's an order that has to respect the fact that 1 is smaller than any other monomial. Okay?
It has to respect the fact that it respects simplification of monomials. Let's put it this way. This is our generic monomial in k variables. x1 to the 1 times x2 to the 5 times x6 to the 72. Okay? I want that for any possible exponents, one is the smallest. Go back to your mathematics and know you understand what this means. Then I want that if I'm shortening notation here. I write x to the alpha. If
Could you write figures?
Yep.
Okay.
Okay, what do you think? If the ratio x alpha x beta is still a monomial, so the ratio has still non-negative coefficients, what do you think? X beta or x alpha should be larger in total?
Are you happy?
Are you happy with this? Okay. So if we have these two main conditions, then we have a way to order, I would say the monomial, somebody else would say all the vectors of non-negative integers of dimension k. Now this is very important. It's also something that we have to deal with as statisticians, because this implies, for example, I invent, okay? This gives also an order, implies an order on my factors. And I don't know if I really want that to happen. I don't know if height should be more or less important, or should be related at all with the number of cars you own. Okay? But we'll see that it doesn't really matter at the end. There is some algebraic theory that helps us to say, doesn't matter, you can work this through. But still, for the theory, having a toe is, even a term order is really fundamental. Okay, so let's go back to the definition of the Grosvenor basis, and while I tell you, make a link with today's lecture, previous lecture. Okay, I consider the leading term the highest for each element of the set that I want to be a Grosvenor basis. I consider the largest element with respect to tau. That's called the leading term, the leading monomial. I consider the monomial ideal generated by these monomials. Okay? Now, I compare it with the analog, the similar monomial ideal, which is not generated, which is generated by all the elements in my ideal. If these are equal, that is, if the leading terms of the set I have and the ideal generate the same thing, then we have a Grosvenor basis. This this fact is equivalent to say that I take any polynomial, I divide it means I take the normal form of this polynomial with respect to the set G, and I do that keeping in mind the ordering tau. Then this remainder of Euclidean division exists unique. These are equivalent facts. And again, this is equivalent to say this fact that I take any element of the set I want of the Gröbner basis, and then the normal form of this polynomial divided by G is again 0. Of course, this G is Gröbner basis with respect to tau, my term ordering. And here, when I do division, I have to respect this term ordering. Now, what we saw today is that the generating sets of polynomials ideas are finite in number. That is, the cardinality of G is finite. So that to check if something is a Gröbner basis, I only need to check this, if you want, a finite number of things. And that's what makes this theory very computational. Okay. There is a very nice algorithm that allows to check if a subset of an idea is actually a Gröbner basis, and that's called the Buchberger-Müller algorithm. I'm not going to explain it now. If you're interested, we can talk in the break or afterwards. Okay? Then I was telling you that it's very annoying to have to deal with this term ordering because it's difficult to give it a statistical meaning. Sometimes there is a natural statistical meaning, most of the times there isn't. But something I was saying comes handy to us, and it's the fact that even if the possible term orderings are infinite, the actual Gröbner bases are finite. This means that by changing this tau, I will obtain maybe many, but only a finite possible vector space basis, canonical vector space basis in this quotient. Okay. Are we okay with this? So I'll move on the next slide, where I'm going actually to talk about vector space basis here. Let's go back to our 5 polynomials describing our sets of 4 points. It can be shown that this is a Gröbner basis with respect to any term ordering. If I choose a term ordering by which x is smaller than y and y is smaller than x cubed, then the leading terms are those underlined here. Let's have a quick check. x4, well, must be larger than x3, then x2, and so on. Y squared, is it, well, I don't compare it with y, it's obvious. I start comparing with yx, yx. So, or maybe as it's written there, and only if, and that's because I asked that to happen to monomials. And you can check this through. And you have to do a final number check if you want. Very boring, but can be done. Okay, it turns out that a vector space basis is given of the quotient space by all those monomials who are not divisible by this. Let's have a quick design plot on the board. Here I just want to draw the exponents of these monomials. So we have 0, 4, 0, 3, okay? Now check what's happening. These are exactly the crosses, exactly those that are not divisible. Okay? 1, 0, 0, x squared, y. I've done it this way, but you can imagine, you can see how these things can be made automatic. And there are interesting algorithms to do that. Now that we have this drawing, let's observe the following. Well, actually, it's better to observe it here. Draw this line. This line is telling me that this basis is hard. It's not very nice. Because, no, actually, sorry, it's telling me that this is very nice because it's a corner cut. For algebra, for algebraic geometry, they like it. It's a corner cut, meaning that I can draw a straight line that is an hyperplane of dimension k minus 1 that separates these empty dots from everything else. It can be seen by my 4 initial points could also, or let's say different, a vector space basis of the quotient space, it's also the following. Those 4 dots, again, which corresponds to these 4 monomials, is again a vector space basis of the quotient space. Unfortunately, it's not a corner cut. This means that I will not be able to retrieve it via algebraic methods. There is all a big theory behind it. But as a statistician, I like this very much because it puts me on the same level the variables x and y. Why I cannot retrieve this? Well, go back here and check if you can have a term order in tau such that the leading terms are if you want, you can add them. There is no way you can manipulate these 5 polynomials to obtain this set. Okay. If this is clear, we'll look at this in another way, in this table here. Our points, our chooser model. This is the design model matrix. What, if you've done any linear statistics, is indicated with a capital X, usually. The model matrix. Now, this tells me that if I take any linear combination of any, well, let's not repeat. I can take any subset of this form and still obtain, build out of that a linear model for whatever output I want, third variable I want to consider. Somebody tells me and say, look, I'm not sure I want x squared. Or it tells me instead, look, I would really like to be able to identify, to estimate, that is to substitute some of these columns with this, x cubed y minus y cubed x, because this is some particularly important. I know that it's expressed feature of my problem that I want to be able to identify and then to estimate. Okay, then what this theory says is that consider the normal form, the division of this, by your Grosvenor basis, and what you obtain is this remainder. Okay, then look at this remainder, and it involves y, x, and 1. It's a polynomial in these three. So the theory says you can substitute any among y, x, and 1 with this. You cannot retrieve this form like this, because you will lose identifiability. You will not have any more a vector space basis. But if you substitute any between y, x, 1 with this strange polynomial, you will have a vector space basis of the quotient space. Of course, somebody can come and tell, look, not everything is a polynomial. I actually want to consider this function. I say, okay, I evaluate this function on my data points, and I realize that it's identical to this one, identical to this one. That is, these three functions, 1, 2, 3, are not distinguishable on my design. Okay?
I have a silly question, probably. What do you mean by division of polynomial? Did you kill the leading term?
Exactly. Division of polynomials is what you think in one variables.
Okay.
It's Euclidean division extended to more variables, higher dimension. The key point in performing it and having a unique, having one and only one remainder is exactly the choice of a term ordering. If you don't have this term ordering, you might end up in loops. You can perform Euclidean division, as you know, from one to more variables, and you end up working at infinity. Instead, if you perform the division following what dividing first and the leading term, then it works. Okay. Yes, this very last line expresses what I was telling you about building out of this a linear regression model. And otherwise, it's all a summary. Okay, let me show here a little example. This was actually a case study that we did many years ago to prove that it has some usefulness. It wasn't only nice math what we were doing. And we had 4 variables, k equal 4. Each one was going to take 3 levels, could be plus minus 1 or 0. And the experiment that at the company they wanted to do was this. Was this meaning, okay, I want to run all. Okay, let me look at this. This is easier to show. Here, it's a bidimensional representation of a full 4-dimensional experiment, where we have, for example, our 4 variables were called AFR, load, RPM, and EGR. This first column represents all the points for which AFR is equal to minus 1. This first row, those for which EGR is equal to minus 1. And then here we have load equals 0 and RPM equals 0. This is a very typical representation for a full factorial. Full factorial means I take all possible combination of 0 plus minus 1, such that I will have 3 to the 4 points. Now, the intended experiment was to do all points here and all points there. The actually performed experiments were only the black dots. this choice came from design reasons that depended on the actual problem studied. Now, if the intended experiment had been carried out, then there are available techniques to study it. But only when the experiment with the black dots were carried out, standard techniques will not work, will lead to solution supported by good, strong theory. So, what we did was to use this Gröbner basis method, this polynomial idea. We built, this is the Gröbner basis for the black dots corresponding to this particular term ordering. And we found, notice this is a term ordering where first I want to include in the vector space basis linear terms, then quadratic terms, third order terms, and so on. And a special order on the variables r greater than L, E, and so on was chosen. So RLE, RLEA. So what was a vector space basis? We just ran a computer here, a click. We would have found the constant term, the linear terms, the second order, r square, ry, and about the third order terms, we only found those that here in the last row are indicated with a star. So the obvious thing was, okay, let's permute the order of the variables by keeping this, by keeping the fact that first I have order 1 monomials, then order 2, then order 3. And what we found that there was variation in the vector space basis only at degree 3. And the variation are indicated here. Basically what we're saying that the vector space basis was rather stable with respect to that choice of families of term modeling. And that was satisfactory enough to build a very good model out of it. Statistical model, I mean. Okay. This is repeating something I have already mentioned, and that's the problem here between being corner cut and not being corner cut. Now, algebraists are very smart, so what they've done is to define a set of points being generic if it's Gröbner-Fan. The Gröbner-Fan is the set of all possible Gröbner bases by varying the term ordering, which, I remind you, it's a finite set. So I want that the Gröbner-Fan is the set of all corner cuts with n terms in k-dimension. Again, this is a computable object. Not very easy. It seems a very easy thing to compute, but actually it's not. Well, there are some interesting papers that work on develop this idea. And again, I will have references at the end for who is interested. Now, if this is okay, I'd like to move on to another interesting set of data points, which are the so-called compositional data sets. What I suppose is that my original points are not in R to the k, but actually they lie in the k-1 simplex. This in particular means that the sum of the coordinates of each point must be equal to 1. That is, in my ideal, I will have always this polynomial. Now, there are various things that one can do. The first one is to say, okay, I can always, wherever I find 1, substitute it with this sum condition. Somebody else could say, okay, but if I perform the algebraic statistics stuff, the one I explained, from design to ideal to quotient space, I will lose one variable. Statisticians say, yeah, that's called the slack model. I can work with it. Or I can use projective algebraic geometry. And use mine, so you know where I'm going to do, where I'm going to go. This is again a simple example. 4 points lying on a simplex Well, I don't associate it to an idea, a polynomial idea, any polynomial idea, but I consider a homogeneous polynomial idea. You see, it's the idea whose variety are actually the lines from these points and the origin. That this is the ideal of the cone that we associate to our points. And then the procedure can start again. We can repeat the computation of the quotient space basis as we did before, with the same problems and the same thing. Obviously, what we'll end up doing is to have, we would like to work order by order. We are homogeneous. So we'll include the constant term 1, here is not even written, then the first order, second and third. And observe, we do not include all of them. Of course, at this stage, we'll end up with an infinite set of monomials. This is not a zero-dimensional variety, the cone. So the vector space basis of the quotient space will be infinite, but will be extremely regular. And out of this regularity, we can build our finite set of monomials that we can use for a linear model. Essentially, I take any 4 of these. Any 4 will do. Okay, how are we with time? This covers pretty much all the main topics related to considering the ideal of points representation of a design. Now I'd like to show another representation, which is indicator function. Now, let's assume, as it is possible, every single finite set of points can be seen as embedded in a full factorial. That is as a subset of a regular grid of points. This is the view that indicator functions take. I say that my set of interest, F, which is a subset of this larger grid, more often than not a very regular larger grid, is represented by a function defined over D, which takes value 1 if I'm in F, 0 otherwise. Now, being D a finite set of points, and being F a function defined over D, I have a representation of it. Because this F is nothing more than a function in the quotient space by the ideal of the larger grid. And this is my representation. So what I'm saying is that I write this F as a polynomial whose linear combination of the quotient space basis that I found before working over D. Here there is an interesting trick that to make things very nice computationally and to have a Galois theory kicking in, one could represent D as code the levels of D and thus of F as the roots of the unity, and working over complex field. There are variations on the theme that now one can do the same thing without using the complex field. Okay. I'd like to conclude, maybe quite not going through all details, by showing that this representation has been useful to work with Sudoku. This might be a bit silly, but actually, Sudokus are examples of Latin hypercube, which are spatial design of experiments who are very important in agriculture, because it allows for crop rotation and avoiding wearing out the soil. Actually, there has been, in the 50s and 60s, a lot of literature related to Latin hypercube and other type of this. Okay, I'm not going to explain what Sudoku is, okay? But I need to stress the fact that there are 4 factors we are interested in. The first one is the row, 1 to 9. The second one is the column, then the box, and of course the symbol. Now, each one of R and C will be split, and the symbols as well, will be split in two pseudo-factors. R will become R1, R2. R1 tells me I'm in the band 1, or second band, or third band. And R2 will tell me I'm in the first row, second row, third row of one given band. Okay? Likewise for columns. Notice, by doing that, I will have, having chosen B equal 3, I will have that R1 takes value 0, 1, 2, R2 takes value 0, 1, 2, 3 factorial. Okay, about the symbol, what do we do? Well, to the symbol S, we associate S the, okay, we consider S minus 1, divided it by P, that is 3, and the two pseudo factors associated to S will be remainder and quotient, S1 and S2. So that's what we've done. We associated our Sudoku to a full factorial design, written like this, with how many points? Well, 3 to the 6. For example, the number 5 in this position is represented by this combination. Okay. What's the next bit of the game? This 3 to the 60, no, sorry, 3 to the 6 set of points describes me all possible Sudoku grids, all possible values, all possible combinations that I can have here. To select one particular grid means to say, okay, I want to retain some of this line and exclude some others. And this is done by imposing that some of the coefficients of the generating function, of the indicator function of my Sudoku, of my subset, satisfy some conditions. First of all, let me repeat what I just said badly. The game rules translate into values of the coefficient of the indicating function of the Sudoku over the full grid. The fact that the fraction has a p to the 4 points, it's represented by the fact that the coefficient of 1 here is 1 upon p squared, because these are the number of cells that I want in my grid. The fact that each cell appears only 1 means that these particular coefficients has to be 0. And now these rules might be a bit mysterious about it at the moment. But actually the mathematics behind them is really easy. It's just once you have the indicator function, once you know what a full factorial is, just go straight, apply the rules straight away. Okay. This is useful to check if a subset of this table is actually a good Sudoku grid. But the problem of Sudoku is to find a Sudoku, maybe subject to some constraints. Okay, this means solve this set of equations. And this is a set of polynomial equations, actually rather easy. Some coefficients are set to 1, some linear, square. Well, this seems like an easy problem, but it could be solved computationally only for p equal 2. Not very clever. Humans are much faster. It will be interesting to move over and to find a fast algorithm to do that. Not to solve Sudoku, obviously, but to apply to the other type of applications. Another thing is, okay, and here is the mention of Markov basis. I've done a Sudoku game, and I want to see how to move from this to this solved problem to another possible solution. How do I do? By keeping fixed maybe some constraints. Constraints are just polynomials because I'm saying that in that cell there should be that symbol. This is possible by employing Markov bases. Markov bases do exactly that. They allow to move over a fiber where some constraints are satisfied. In particular, the moves that are considered here are permutation of symbols, permutation of bands, of rows within bands, likewise for stacks and columns within a stack, and transpositions. I repeat, it's interesting that at each one of these moves there is only one polynomial corresponding. And if F1 is the indicator polynomial of a Sudoku design, M a polynomial representing a move, then F1 plus M, this polynomial, the indicator function, F1 plus M, is still an indicator function. M is a polynomial that lies in the ideal of D, so it takes a value 0. Then F1 plus M is a new Sudoku grid. Okay, now in the very last minute, I want to tell you that in the next hour we'll talk about this. I will have a twist in my situation, in my setup of the problem. That in the last hour we'll talk about this link a bit more. And let's say, well, each line on this table represents standard, classical statistical problems that have been tackled by an algebraic viewpoint, that is with the techniques I just described. Let me see. No, I don't have it here. On the references, I wanted to to cite as a reference this book, which is actually a textbook on algebraic geometry. And Cox Litology, you can find the PDF online. Shouldn't say that, that's what it is. And what the Professor Riccomagno explained this morning, what I didn't tell you about is underlining all what the applications I've shown is actually in the first 4 to 5 chapters of this book. And here in this slide, instead, I wanted to give some general references to these are books on this field, algebraic statistics. The last one just came out. It's from a postdoc of mine who is using semi-algebraic statistics, meaning he has